The brain needs no introduction. After all, the brain is what makes you, you. But it is a paradox that the organ that lets you understand the world understands so little about itself. Now, thanks to stunning research building upon decades, no, maybe centuries of investigation, science is peeling away the layers of mystery to reveal how 3 pounds of flesh create an entire universe inside your head. In this corrugated mass, a staggeringly complex symphony of electrochemical reactions play out every second of every day. Much of it does so without a conscious conductor. The brain makes the lungs expand with the inrush of air and the heart pump blood. It houses memories, processes sounds and sights, smells and tastes, and feelings ranging from the subtle to the sublime. Beyond the work the brain does automatically comes something far different. Out of the human brain arises consciousness and the mind, the unique ability of Homo sapiens, or the thinking man, to be aware of being aware. Welcome to An Essential Guide to Your Body and Brain, our series that we just started last week. Last week we started with the body, today it's about the brain. And we're going to focus in today's episode on the learning brain. We're going to talk about neurons, how they work, how they communicate, the language, how we learn, the memory, the problems with our memory. A lot of things that have to do with learning, the learning brain that you need to know. And this is going to be the part where we focus on the brain. And throughout the series, we're going to focus on different aspects of the brain. Now, today it's going to be about the learning brain. We're going to focus on the perceptive brain, the unconscious brain, the emotional brain, and finally the aging brain later down the line in the series. And this is a new episode from our series, An Essential Guide to the Body and Brain. This is your host, Danny, and this is English Plus Podcast. Now, before we start, let me remind you that you can find the transcript of this episode on the website. The link is in the show notes. And while you're on the website, you can explore the website for the many learning opportunities you can find there. And it's not just about learning, it's also about having fun. Remember, English Plus is about a variety of things, so you can find a lot of different things. And I'm very sure that you'll be interested in learning more about at least one of these. So take your time, explore the site, and of course, as I told you, the link in the description will take you directly to the transcript of this episode. And now saying that, let's not waste any more time. First, before we start talking about the learning brain, I'm going to give you a little introduction to the brain itself. That's coming next. Don't go away. The human brain and its consciousness contain many mysteries. In recent centuries, scientists have used an increasingly sophisticated variety of tools to find out what happens where, though much is left to learn. We still don't know a lot about that, but we've come a long way, I would have to say. A quick tour begins with the brain's protective structures. The crown of the skull is a collection of 22 bones that house the brain and protect it from harm. Inside, 3 membranes provide more layers of protection: the dura mater, the arachnoid, and the pia mater. Flowing between the arachnoid and pia membranes is the brain's cerebrospinal fluid. Fluid-filled ventricles curve deep into the brain and connect to the spinal cord's central canal. Cerebrospinal fluid cushions the brain and provides nourishment for tissues. So what about the other parts of the brain? Well, by evolutionary reckoning, the oldest portion of the brain is its stem, which begins as an extension of the spinal cord. The brain stem controls basic physical actions necessary for survival, such as heartbeat and respiration. It is home to many sensory and motor nerves, the latter named for their function of controlling movement in muscle tissue. Motor neurons also densely populate a second part of the brain, the cerebellum, at the back and bottom of the skull. The cerebellum coordinates precise voluntary movements such as tying a shoe or playing a violin, and also plays a role in emotion. A third component known as the diencephalon lies in the brain's center. It controls the body's rhythms of sleeping and wakefulness, regulates involuntary actions of the nervous system such as digestion, and relays sensory stimuli to other brain regions. So what about the cerebrum itself? Well, that's the fourth region, the cerebrum, and that is what most people think of when they envision the brain. It lies in two hemispheres, left and right, connected by a band of tissue called the corpus callosum. Although they look alike, the two halves perform and control very different functions. The left hemisphere has long been considered the dominant half because of its role in processing language, but the right hemisphere is gaining new attention for its role in emotions and spatial cognition, as well as the integrative function that helps bring bits of information together. So what about the cerebral cortex? The cerebral cortex is the outermost brain layer, folded and wrinkled and resembling a squishy pink walnut. The cortex is home to the higher functions, reason, creative thinking, and language that separate the human brain from those of other animals. The amount of neurological firepower necessary for such exploits is considerable. Of human brain mass, 76% lies in the cerebral cortex, the greater percentage than that of any other animal, and within the cortex lies about 75% of all neural connections. The cerebral cortex processes information so that you may comprehend enough about the world to survive. Evolution and experience have molded the cortex's neural connections to favor sensory and cognitive functions that have proved successful over eons of human life. Anything that challenges your brain's time-tested circuitry opens a window onto hidden depths of self-knowledge. So that was a very, very short introduction to what the brain is all about, or of what it consists, but that's just the tip of the iceberg. We're going to talk in more detail about a lot of brain functions and very interesting, exciting, and I bet things you've never known about before, things that are right inside your head. And as I told you today, we're going to focus on everything that has to do with the learning brain. And that's what we're going to talk about next, so don't go away. I'll be right back. The brain constantly rewires itself to become an organ that is physically different from what it was the preceding moment. Never resting, it churns through new experiences daily, incorporating some into its network of stored information and discarding others. The creation of memories creates personal and social identity. When disease and disorder rob the brain of memory and language, they take away what makes each person unique. Learning and memory work together. Some learning is transformed into lasting memories. Other experiences prove ephemeral. Eric R. Kandel, who received a Nobel Prize for research on the molecular foundations of memory, draws this distinction. He says, learning is how you acquire new information about the world, and memory is how you store that information over time. Learning includes not just cognitive components such as solving quadratic equations, but also motor components such as tying a necktie in a perfect Windsor knot, and affective components such as feeling shame at a social faux pas. So that is in a nutshell what we're going to talk about. But in a nutshell, not in detail, because details are coming. But in order to understand how learning happens in the brain, we're going to start with the very basic brain cells. And that's coming next, so don't go away. I'll be right back. Reading, learning, pattern recognition, and so much more all begin with the fundamental unit of the brain, the nerve cell or neuron. Some chains of neurons send information to the brain from the body's extremities. Others send information from the brain to the body. Still, other chains share data among themselves to construct subconscious or conscious thoughts and feelings. And maybe you've heard of things that are called axons and dendrites that are related to brain cells. But what are these? Now, each neuron contains a cell body with a long tail-like fiber called an axon, which sends electrical impulses to other cells. Some axons are short, extending only to adjacent cells in the brain. Others are much longer. carrying impulses down the spinal cord to move the arms, legs, and feet. Axons may split and branch into as many as 10,000 knob-like endings that disperse impulses across many cells. Each neuron also extends into networks of dendrites, which are thin, short fibers that transport electrical signals to the main body of the neuron from outside sources. The human brain contains perhaps 100 billion neurons. Each links to so many others that the entire network forges literally trillions of connections, making the brain the most complicated object in the universe. And now, before I move on and talk about neurotransmitters, I have something very interesting for you, and that has to do with exercising your neurons. Well, both the brain and the body need regular exercise if neurons are to remain sharp. Repetition of newly learned tasks helps make neurons' connections stronger, but use it or lose it also applies to physical stimulation of the brain. Like other organs, the brain works better when the body is healthy. Exercising regularly appears to help ward off Alzheimer's disease, as do reducing body weight, lowering blood pressure, and eating a more healthful diet. To spur on the brain to make new neuronal connections and protect the ones it has, try such activities as learning a new language, listening to classical music, solving mental puzzles and games like crossword puzzles and Sudoku, eating a healthful diet, and finally walking, jogging, or cycling regularly to promote cardiovascular health. So, that is very important, and that will help you improve this mental muscle you have. Of course, we don't have muscles in the brain, but you get the point. And now let's move on and talk about neurotransmitters. And that's what we're going to talk about next, so don't go away. When a neuron sends an electrical discharge along the length of its axon, it halts at the synapse like a car at the edge of a cliff. There, the impulse activates electrically charged molecules stored in the neuron's cell wall. These molecules, known as neurotransmitters, leave the membrane of the first neuron, move across the synaptic cleft, and dock at a second neuron. The receptor cell surface contains specially shaped docking sites, so particular neurotransmitters can dock only at the appropriate places. The arrival of a neurotransmitter alters the electric charge at the edge of the new neuron and sparks a new electrical impulse. It travels the length of the new cell until it reaches the synapse of another receptor cell and starts the process all over again. So we're talking about electrical networks here, right? As impulses pass among complicated chains in the central nervous system, they form networks that specialize in performing particular functions, such as understanding language, remembering experiences from the past, and comprehending the outside world. All information processed by the brain is nothing more than electricity passing through neuron after neuron and passing only to be converted into chemical energy as it leaps across each synapse. Dozens of neurotransmitters have been identified and more discoveries are expected. Certain neurotransmitters make muscles contract, help regulate sleep, and block pain. Neurotransmitter disorders have been linked to Parkinson's disease, depression, Alzheimer's disease, schizophrenia, and a host of other illnesses. So that's how the neurons communicate with each other and form those electrical networks that are active all the time within your brain. And now let's talk about something a little different, and that will help us understand more about what comes next in this episode when we talk about language and memory, and that has to do with the growing brain. That's coming next, so don't go away. The nascent brain makes its first appearance about 4 weeks after conception, when a thin spoon-shaped layer of cells called a neural plate emerges at the head end of an embryo. As the fetus grows, swelling in the original spoon shape eventually become the major sections of the brain, from the cerebrum at the top of the head to the thalamus, hypothalamus, cerebellum, and spinal cord at the back and lower end. And within this process, something extraordinary happens that is called neuron migration. The most dynamic growth occurs in the cerebral cortex, which is the outermost layer of the brain. During early fetal development, when about 250,000 new nerve cells are being created every minute, neurons begin to take on specialized tasks. First, they inch their way from where they were formed to their permanent home in other regions of the brain. Most go toward the cortex, but some move into the cerebellum and other portions of the brain. This process, known as migration, is remarkable for the distance the neurons must travel, as well as their ability to navigate along the tangled pathways of the developing brain. Millions of neurons migrate a distance equivalent to a person hiking from Los Angeles, California to Boston, Massachusetts. Can you imagine that? And this is called neuron migration. But that's not even close to the remarkable things that happen within your brain that we're going to learn about in the series. And one of those things is the thing that happens next, and that is survival of the fittest. Well, the brain of a fetus at about 8 months after conception weighs only a pound, which is about a third of an adult's, but contains twice as many neurons. The brain cannot sustain biochemical reactions across all of its neural connections, and so the weakest of them begin to die through a process known as pruning. In the last stages of fetal development, about half of all neurons die. At birth, brain development expands to include processing responses to new experiences like sights, sounds, smells, actions, and emotions. Networks of neurons compete for survival as environmental stimuli strengthen some connections while others wither. So, it is survival of the fittest, even inside your brain, because not every single neuron was meant to survive. And now that we have learned how the brain grows, it is time to talk about memory, which is one of the most important and sometimes puzzling things in the brain. That's what we're going to talk about next, so don't go away. I'll be right back. Without memory, people would live in a never-ending now with no ideas of where they have been or where they might go. The memory of representations of the world gives humans the unique ability to think about the past, present, and future. Scientists who study memory find it a tough nut to crack. Neural circuits responsible for memories lie scattered throughout the brain. Experts have found some brain regions to be particularly crucial, however. The hippocampus, so-called because it resembles a seahorse, and the word hippos in Greek means horse, so that's why it's called the hippocampus. But anyway, the hippocampus plays a significant role in emotion and memory. Lying deep in the forebrain, it receives sensory data from the senses and integrates them into a single experience. I bet that most of you have heard the terms working memory and long-term memory. So what's the difference between these two? I mean, sometimes it's nice to nod our heads to something. Oh yeah, working memory, long-term memory. But do you really know the difference between these two? That's what I'm gonna tell you. And by the way, that's what I hope this series is all about. It is about to let you know of these essential things that you might have heard before, but you don't know for sure what they are without the complexity of going too scientific about it. It is something that everyone can understand, but at the same time, people who are interested in science might find a thing or two they haven't heard about before. So let's continue and let's talk about the difference between working and long-term memory. Some memories last less than a minute, and some last a lifetime. Working memory, which is a type of short memory, holds sensations for a few seconds. You remember the last few words you spoke or the last few ingredients you put in the stew so you may complete the tasks you have begun. Then working memory clears and you move on. Long-term memory is a different thing. Long-term memory is more like a filing cabinet. Some documents from a computer screen or a tabletop get filed for later use. Information is more likely to make the transition from working to long-term memory if you pay particular attention to it, repeatedly try to remember it, or associate it with strong emotions. These memories are useful not as much for navigating through the moment as for making good choices and succeeding at life. So, can we say that one is more important than the other? Absolutely not. Both are very important and both are there for a good reason. We don't want to remember everything. We want to remember the things we are interested in the most. So, if we can do only one thing or the other, we can't do either, if you know what I mean. We will need the working memory to be able to go on with our daily tasks, but then we need to transfer some of those memories to our long-term memory because these things are important for us in the future. These memories that we focus on and we try to learn, and that'll become part of our long-term memory, will help us make better decisions. That's why it's important. But the most important thing is that you know now the difference between working memory and long-term memory. But that's not everything we're going to talk about when it comes to memory. Next, I'm going to talk about memory categories. So don't go away. That's what we're going to talk about next. I'll be right back. Although a keen observer could no doubt create a very long list of attributes for a delicious red apple, the information would fall into 4 categories of memory: sensory, motor, visual, spatial, and language. Now let's start with sensory memory. Sensory memory involves the 5 senses, with smell as the most powerful memory trigger. As the senses create our appreciation of the world, it is not surprising that many memories can be recalled via sensory cues. A certain song, for example, might bring up memories of a wedding or family reunion. People with powerful memories often create visual cues in their imagination to increase the strength of their long-term memories. So that was about the sensory memory. What about the motor memory? Motor memory provides fine motor control for practiced actions. These include everything from the subtle controls over the vocal cords to produce speech to the motor control that underlies the complicated act of walking without losing one's balance. Motor memory is tied to the learning of skills. Damage to brain areas that affect one invariably affect the other. Recent research suggests that motor memory's application to learning new skills takes place in 2 stages. The first stage recruits neural networks that best represent the motions required for the skill, such as eyes, ears, and fingers for playing a piano. The second stage occurs after the basic motions are mastered and implicitly memorized, when the brain recruits additional neurons to refine the motions. That's the difference between the adequate performance of a weekend musician and one who practices for a seat in a symphony orchestra. So that was about the second category, the motor memory. What about the visual spatial memory? Visual spatial memory combines the neural pathways of the visual cortex and the spatial orientation of the temporal lobes. The left hemisphere is significant in perceiving details, while the right hemisphere works to integrate the details as a whole. Together, they let you see the trees and the forest, which is very important, of course. So that is the visual spatial memory. And what about the last category, which is the language memory? Language memory leads to the ability to associate words with objects, which is the crucial foundation of communication. The grounding of communication in the brain's hardwiring to acquire language can lead to serious consequences from verbal memory disorders. These can not only interfere with communication, but they also can distort with perception of reality of someone who may be unable to discriminate between statements that have a source in true memories or those that draw on fantasies. Unable to tell the true stories from the false, these people may struggle with the concept of truth. The process of remembering by retrieving information from storage and then restoring it colors memories with additions, subtractions, and substitutions. The more time that has elapsed since an event, the more likely the brain has rearranged the memory of it. So that tells us that this is not to be trusted because it can change and not on purpose. Your brain can do it on its own, especially if a long time has elapsed. So while it is, of course, important to rely on memory, but we understand now that memory is not that reliable. And people can add things, subtract things, or substitute things in real memories, rendering them unreliable in the process. And that is what I'm going to talk about next. I'm going to talk about unreliable memory. Not exactly from this perspective, but also from other perspectives. We'll talk about amnesia and false memories. That's coming next. Don't go away. Memory disorders, which range from the transient losses of concussion to the devastation of dementia, can have a profound effect on a person's sense of identity and reality. Now, let's start with amnesia. And by the way, when I say amnesia, it's not just one thing. It is a lot of things. And here I'm just going to give you just one example. Now, for example, a bizarre disorder of memory typically caused by alcohol abuse, called Korsakoff psychosis, eliminates the brain's ability to create and store new memories. If you meet a patient with Korsakoff's, chat for a few minutes and then leave, the patient won't recognize you when you return. However, if you suggest that you've met before, he or she will fabricate a story to describe the previous meeting. Very destructive and very weird, to be honest. But that happens, and it is one type of amnesia, of course. Now, talking about amnesia, of course, I'm not going deep into that, but you will have to know that amnesia has nothing to do with what we see in movies. Except for very few movies like Memento, for example, which portrays amnesia as it should happen. Because amnesia is not like what most people think. It's not about just forgetting about the past and just going on from this moment forward as a normal person. Amnesia is just the opposite. You might or might not remember things from the past. You might remember a lot of things from the past, by the way, but the thing that is damaged is that you cannot create new memories. You cannot generate new memories. So you lose this ability from this moment forward, not the other way around. And as I told you, there are a lot of different types of amnesia. Korsakoff psychosis is just one of them, but a very good example. And now let's talk about false memories, which is not exactly amnesia or a kind of a problem or disorder, because this is common in healthy people. In one experiment, Elizabeth Loftus gave adult subjects lists of things that really happened to them as young children. However, Loftus added a lie to the roster. The subject had gotten lost at a mall. About a quarter of the participants said they remembered the false event, and many gave elaborate details. And here Loftus says, people's memories are not only the sum of all they have done, but also the sum of what they have thought, what they have been told, and what they believe. So that's why memory is unreliable. Even for healthy people, even if you don't have a disorder or problem or an injury of sorts, you still run the risk of relying on your memory. Of course, you have to, but you don't rely on it like 100% because there's a great possibility that you can add things or even imagine things or create things from scratch, not with bad intentions, but that's how our brain works. So that is about unreliable memory. And what's next? We're going to talk about language. That's coming next. Don't go away. That's going to be very exciting and very important for you to learn about. I'll be right back. Language, including speech and reading, is so important to human survival that it accounts for a massive amount of cranial space. Now let's start with reading and listening. Reading letters silently on the page initiates action to sense the shapes of letters and words in the primary visual cortex at the back of the brain. It also places demands on working and short-term memory to hold those words long enough for the reader to make sense of how they form sentences, as well as analytical functions to pull those sentences apart for meaning. When a child hears words spoken aloud, the auditory association area of the brain is activated. Understanding speech requires encoding and decoding of language in the receptive language areas, which take in signals from auditory association areas and, if the words are seen on a page, from the visual association areas. A parent reading aloud uses a different brain circuit from that of the child being read to. Reading generally begins with activation of the visual cortex, which sends signals to Wernicke's area, whereas speaking aloud activates an adjacent region called Broca's area. Reading aloud requires the cooperation of both these areas. And now, since we talked about children and language, let me just tell you about an interesting thing that has to do with children and language. And that is about children who are raised in a home where two languages are spoken. Now, if that happens, they grow up fluent in both and don't have an accent. Adults, on the other hand, often struggle to pick up a second language, and even when they succeed, they don't usually sound like native speakers. The difference lies in the greater plasticity of a child's brain. Young children recognize a greater range of language sounds than adults. They pick up vocabulary and syntax more easily, and they process languages more effectively, activating smaller regions of their brain than do adults learners. But saying that, and although that we know the brain is particularly sensitive to learning languages at a young age, it's never too late to benefit from the mental gymnastics of wrestling with a new tongue. Adding a second language improves cognitive skills and memory, as well as exposes learners to new ideas. So, try to do it no matter how old you are, and never say to yourself it is too late to learn a new language. Learn a new language not because you want to go there, not necessarily because you want to go to that country or you want to speak that language, but it is one of the best mental exercises ever. And to be honest, it's always useful to learn a new language, no matter what that language might be. So you might want to use that to strengthen this mental muscle of yours. And now let's get back to what we were talking about, and let's continue talking about the learning brain and language. Now let's talk about the evolution of language. Although some scientists believe the mind can exist without language, others argue that language produces mind. And here I quote Derek Bickerton, who is an expert on Creole languages. He said, "Without language, I wouldn't say that it is impossible to have mental experiences, but I'd say the mental experiences would not be very coherent." Now, according to Bickerton, Pidgin is the first developmental stage in the creation of language. Pidgin languages, from when people come together who cannot communicate in a common tongue, such as slaves taken from various tribes of West Africa and placed in the New World. Pidgin assigns words to objects but lacks grammar and thus complexity. For example, arrow deer. Arrow deer might be a command to help kill a deer or an announcement that a hunter has just done so. Bickerton believes that the increasing complexity of a child's brain and its accompanying ability to master speech may mirror the evolutionary history of human language. So we talked about language and human communication. What about animal communication? Now, even animals have developed their own complex ways to communicate. Whether acoustic, visual, chemical, or tactile, each animal's choice of communication method relies on its strongest and most sensitive neural receptors. Animals, like humans, also can combine sensory stimuli for more sophisticated communication. The great apes, closest to humans in evolutionary development, possess a communication system that incorporates gestures, postures, expressions, and vocalized sounds. The Gorilla Foundation taught a lowland female named Coco about 1,000 words of American Sign Language. So I hope you're learning a lot and you're having fun at the same time so far. We still have two things to talk about. We'll talk about disorders, especially we're going to talk about stuttering and dyslexia, and finally we'll talk about intelligence. We have these two left in today's episode and in our focus today on the learning brain, so don't go away, stay with me because that's coming next. I'll be right back. Many common disorders involve the complex tasks of speech and reading. Now we're going to talk about only two, stuttering and dyslexia. But of course there are more, but maybe these are the two most common or the two most known to people. So let's start with stuttering. Now, until recently, doctors considered stuttering a nervous or emotional condition. Now the condition that affects about 3 million Americans falls squarely in the realm of neurology. Stuttering usually begins between the ages of 2 and 6, as children accelerate their learning of language. 3/4 of those children spontaneously lose their stutters. The exact cause of stuttering has eluded research, but it's believed to have a genetic component. Brain scans of people who do not stutter show speech processing most often performed in the left hemisphere of the cortex, whereas people who stutter have an unusual amount of activity in the right hemisphere. But for people with stutters, don't panic. And if you have children that stutter, don't panic because there are solutions. I'm not saying that I know the solutions, but there are experts who can help you. And I will give you a very good example. Now, you must know the famous actor James Earl Jones. James Earl Jones overcame his stutter to achieve fame as an actor and a famous voice. So, if he could do it, obviously anybody else can do it. It's not easy, but it can be done. And the same goes for dyslexia, which we're going to talk about next. Learning disabilities result from faulty reception, processing, and communication of information within the brain. One of the most common, dyslexia, is a disorder of language processing. People with dyslexia struggle with decoding phonemes into words that have meaning. Some have difficulty holding sounds in short-term memory. Researchers focus on a variety of possible causes. Physical impairments of the angular gyrus and the rear of the left hemisphere, which is active during reading, have received attention. Functional MRI scans of people with dyslexia revealed decreased activity in both parietal and posterior temporal lobes. Many people with dyslexia are artists and musicians. Research suggests they may have enhanced abilities to hear bass notes and see sharper colors in peripheral vision. And while that's only a theory, it makes sense, and it may be true. But there's still a lot to learn about these problems and how they occur and how they can be fixed, maybe. And that's why the field of neuroscience is such an exciting field. And even if you're not an expert, or even if you haven't studied neuroscience, I mean, I haven't, but I'm so interested in this field because it kind of helps you explain to yourself who you are. And how exciting is that? For me, it doesn't matter if you know everything about the world if you don't know anything about yourself. And maybe that's one reason that drove me to create this series, an essential guide to your body and brain, because it is very important to meet the closest person to you, which is you. You need to know more about that person first, and then maybe you can learn about other people. Or obviously, you can do both at the same time. But anyway, let's move on to our very last section of this episode. And in this section, we're going to talk about intelligence. And that's coming next. Don't go away. So, intelligence. And when it comes to intelligence, I know everybody thinks about IQ, right? And this might be true to some extent, but it is still very difficult, if not even impossible, to define intelligence. But let's not make this philosophical. Let's talk about it as scientifically as we can. Now, although IQ tests have been in use since the 1900s, neuroscientists still don't agree on just how to define intelligence or on how much of it is genetically determined. Some early IQ tests measured knowledge of facts, which is a function of education and memory rather than the ability to reason. In general, however, a person's performance on a problem-solving test is a good predictor of performance on a wide range of mental exercises. Scientists use the term G-factor when discussing the general measure of mental ability found in vocabulary size, mechanical reasoning, and arithmetical computations. They relate it to the properties of efficient neural functioning rather than knowledge in its own right. The prefrontal cortex, right behind the forehead, is the most likely home for many of the neural processes associated with the G-factor. When it's damaged, a person suffers a variety of impairments to abstract reasoning, and it lights up during brain scans taken during some intelligence tests. But the question still stands: what is the role of heredity? Genetics seems to play a role, but not an overwhelming one in intelligence. Identical twins separated at birth and raised separately in similar environments show a 72% correlation in intelligence. Perhaps heredity sets an upper limit for intelligence, which then becomes subject to other forces. Political scientist James R. Flynn noted that IQ scores have dramatically increased over the past several decades in many countries. He attributes the so-called Flynn effect not to genetics, but to increases in modern humans' ability to solve abstract problems, possibly from living in a more intellectually stimulating world. So that was about intelligence, but remember, we talked about a lot of things today. We talked about the cells, the neurotransmitter, how the brain develops. We talked about language. We talked about memory, intelligence, some disorders, how unreliable our memory is, a lot of information. So if you kind of skipped ahead, I highly encourage you to go back and listen to the whole episode. And with that being said, that'll be the end of today's episode. I know it's a long episode, but it is worth it. And trust me, I kind of chose the most important things you need to know about when it comes to the learning brain, because that is a huge field in its own right. But I hope that I gave you a good introduction that might pique your curiosity to read more about the topic. And I hope you do that, because that's the point of all the series that I'm creating. There's no way in the world I'm going to cover everything. But if I get you interested enough, to learn more on your own, to make you follow the motto of English Plus, and that is never stop learning, then I know that I did my job right. But anyway, I hope you enjoyed the episode. Don't forget that you can find the transcript of the episode. The link is in the show notes. And with that being said, this is your host, Danny. Thank you very much for listening to another episode of English Plus Podcast. I will see you next time.